Okay, so hi everyone. Thank you for joining us today for our second speaker series event. My name is Alika and I'm a co-director for our fall speaker series.
All right, so I'm Helen and I'm also co-director for this term speaker series.
So a little bit about Waterloo Engineering Speaker Series. It is an event run by engineering students for engineering students and really all of Waterloo's students. We aim to bring in speakers each term to give it an engaging and interesting presentation about how they got to where they are, their research and work, and really any other topic of their interest.
And just a few notes before we start. So first, we kindly ask everyone to keep their mic muted and videos turned off during the entire presentation. And please keep all your questions towards the end. And at the end, we'll be taking questions from the chat box, or then we'll allow you to unmute yourself.
So today we're honored to have our guest speaker, Dr. Holly Dole. Dr. Dole obtained her PhD in chemical engineering from the University of Ottawa in 2016. She is currently a research scientist at Natural Resources Canada while teaching part-time at Algonquin College. Today, she will give us an overview of post-combustion capturing of carbon dioxide and utilization at pilot scale, with a focus on the process of converting CO2 to valuable fuels. So it's a very exciting and interesting talk today, and I'll pass the virtual stage to Dr. Dole.
Thanks, Alika. I think I gave you a mouthful to say in the introduction. But yes, so my presentation today is all about, well, not all about, but what I will get up to is how I ended up in the research field of trying to convert carbon dioxide emissions from what I want to say is bad to better. So I'll go through how I even ended up as a chemical engineer, because my journey was not what I had planned at all when I was in high school, and then how I became a researcher. And as most of you might know, CO2 is a big hot topic, and especially even with the pandemic going on right now, they keep talking about this is our chance to change the way we're doing things. So it's an opportunity to shift. So I hope this will give you some good insight. So just to start on who I am, it kind of leads to how I ended up where I was, but this is where I ended up. Professionally, I do work at Natural Resources Canada as a research scientist. I also teach at Algonquin College in 3 different programs. Right now just virtually, so that's been an interesting switch. I did do my PhD in chemical engineering. I also did my undergraduate degree in chemical engineering, and I did the CoOp program in that, which I'll talk about a little bit more later. I ended up deciding to do a master's and then got convinced to do a PhD. So any questions in between all of that, I'm open to hearing afterwards. I'd like to also show you what I want to call is the real me, because it kind of explains some of the background. I grew up in a small town. Coming to Ottawa was actually quite a big deal when I was leaving high school, so that was a big change for me in itself. I originally never knew what engineering was. I grew up in a very trades family. My dad a mechanic, brothers carpenters, and my mom, she's a personal support worker in a nursing home. So very practical people. I like the hands-on part of things, but I had a lot of influence that I'll share that led me into the engineering. It wasn't necessarily my parents. My parents were very encouraging for me to do whatever I wanted to do, but they did not know also where engineering was going to take me. Some of the things I do in my spare time, which shows, I like to think that it shows that I'm just not an engineer. I actually teach Zumba, and I do fitness classes on the side right now virtually. I'm like to be active. I also sew, which I've been sewing a lot of masks lately as well, for like the Ottawa community. Love baking and cooking. I think that goes along with being a chemical engineer in a way. And I do renovate my house, so some of that tradesy family stuck around in me as well. But the real big question that a lot of people ask me is, how did I know I wanted to become an engineer if I didn't know what an engineer was? Well, simply put, I was born with a wrench in my hand. Just kidding. I really wish it would have been that easy, because yeah, I changed my mind, I think, throughout the entire time that I was in elementary school to high school of what I wanted to do when I left high school. The real kind of influence started, this I want to say was what my grade 8 teacher looked like, but not quite. But he was the one that put in my head, and put in my mom's head, that I was good at math and science. So he said to her, you should think about becoming an engineer. This was in grade 8. My mom didn't have the heart to tell the teacher that she had no idea what that meant, but she put that in the back of her mind. Then I got into high school, and it was my chemistry teacher that really noticed that I really liked chemistry, and he was the one that was, have you ever thought about chemical engineering? He even helped me to go to a program called Shad Valley. I don't know if some of you have heard of that, which is where I actually got to see engineers that work in the field, got to talk to them, and that's what really kind of helped the decision. But to be honest, grade 12, I was stuck on these two career paths. I either wanted to be a fashion designer because I'd been sewing since I was 9 years old and thought like that was a path that I could take. And then I have in the other side, my chemistry teacher telling me, well, you should become a chemical engineer. Like, it's a great path. It was ultimately this Shad Valley that helped me narrow it down to chemical engineering. I never gave up my sewing ability. I do that as a hobby. Maybe someday I'll switch to that as well. I don't know. But yeah, so far chemical engineering was the decision maker. And just to show you my 10-year journey, so I decided to go to Ottawa U. It was because it had a co-op program. I also decided in grade 12 that I didn't want to go too far away from home, but far enough that I was away from home. I still wanted to be able to go home maybe to do my laundry or go get food from my parents' shelf. So yeah, I didn't venture too far, but yeah, ended up at Ottawa U, took 10 years, did undergrad, master's, PhD, finally finished. In amongst all of that, so I mentioned that I did the co-op program, and the co-op program is what made me end up choosing to go into research. So when I started my engineering degree, I had this plan that I was going to do a 4-year degree, do co-op, get the experience I needed to get a job right away. I wanted to finish school as fast as I could, and I ended up doing a PhD. But yeah, so the idea was to do the undergrad, finish it, but what happened is that I ended up doing these co-op placements that were all research related. I was always drawn to a research position. So at ACL, I believe it's called CNL now, but at the time I was doing research in nuclear facilities, so new next generation reactors, and so I was doing material testing for those. And I got the opportunity at Iogen. They were doing research for an ethanol plant, so they were trying to scale up an ethanol plant with Shell, and so we were doing part of the research in that process. And then at the Royal Canadian Mint, this I found actually the most exciting part, because I got to see sort of the end product, or the final part of the research, is we were trying to figure out a way to make low denomination coins like the penny or the dime or nickel a lot cheaper. So many of you probably know about the penny disappearing because it was too expensive to make. It cost more than what a penny. And so one of my projects was to create that to be a lot cheaper. We did manage to file a patent. I don't think it made it before the penny got chopped, but we still have the dime and the nickels, so I'm sure they're using that process at this point. So that was kind of exciting. But like I said, all of these, they were all research related, so it kind of fueled at the end of my 4th year when I was deciding, do I go get a job or do I start a master's? I ended up choosing to start a master's because I wanted to do more research, and just that excitement of discovering something new was kind of burning inside of me. And so after I did all of that, actually while I was finishing my PhD, I got the chance to teach at Algonquin College part-time. I did not know that I would go into teaching. It was not part of the plan at all either. And it just sort of happened. Somebody that I was a TA for in my graduate studies, he noticed, it was a professor that also taught at Algonquin and Ottawa U. He noticed that I seemed to interact with the students well, so he's like, hey, do you want to try teaching? I was super nervous to teach my very first class. This is what's actually shown in this picture. That was my first class ever at the college. And then I've been teaching there ever since in different variety of capacity. I also did get the chance to teach at Ottawa U in my last year of my PhD, or last semester of my PhD actually, the first year chemical engineering course, which was interesting, but it was 180 students. And the reason I've always been drawn to the college is because the smaller classes, so I get to actually know the students. I had a really tough time not being able to remember 180 students' names at the university. So that was challenging for me, but I still enjoyed the teaching side of it. So yeah, after then I did a postdoc at Carleton University for a short period of time. It was actually in the mechanical engineering department, but it was environmental related. So it was related to what I was doing in my PhD. And then I ended up where I am today. I started as a research scientist at Natural Resources Canada. And yeah, that is my journey over that. That was over, actually, I guess, what has it been? 14 years now, all the way up to that. So getting to what I do at Natural Resources Canada. So just to give you a little background, if you haven't heard of Natural Resources Canada, it is one of the departments in the Government of Canada. And specifically where I actually work, I'm part of what's called CanMet Energy Ottawa. And so I'm just showing you a picture in Ottawa of the campus. Not all those buildings are CanMet Energy, but quite a few of them are. And it's a technology center. So unlike, I would say, some government departments, CanMet Energy, we have big pilot scale facilities. So a lot of these buildings house like few stories tall pieces of equipment that we do research on. So it's kind of the unique side of this part of the department. So we usually help industry or academic partners to do scaled up versions of them, of their research that they're doing, or to test some sort of new technology they'd like. So it is very engineering, and I would say it's one of the departments where it's what you think when you're talking about engineering. One of my main research focuses, so like the title of my presentation, it's all about carbon dioxide. So everything we do, carbon dioxide plays a role in it. And what I'm going to talk about today is the technology we use, or that we're researching, to try and capture it, and then also try to use it into something useful. Before I get to that, just to give you an idea of what my day kind of includes, like I was mentioning, it's kind of when I was thinking about what an engineer does as I was going through undergrad. It is what we do in a day. So in any day, we might be designing a new system that involves creating process and instrumentation diagrams, so all the different components of the process, what's involved, what kind of instruments you need to be able to control, say, the temperature, the pressure inside of things, the flow. So you're always trying to make something new come out. We also build and modify systems. So when I'm not doing things at the desk, I'm inside the plant. Actually, that's where this picture is taken from. I might be modifying the system. So say if we wanted to add another process stream to bring in a new gas to our reactor. So you get all the components, put it together. We do have a technologist that helps with that, but I have been trained to be able to put all those components together as well. It's almost like adult Lego, I like to call it. Other things we do, so once we have these equipment set up, we do experiments, so we're testing new parameters. We might, in the case that I'm going to talk about later, we're testing new catalysts, so I'll develop a new catalyst, put it into the reactor, and see how well it performs. Of course, along with experiments, you have to analyze the data. So just figuring out from everything that you just did it work well? And that comes into the technical writing. So once you have all your data, you're writing papers or technical reports to summarize all of that. Never did I think going into engineering that I would write so much, but I would say that's at least 50% of my job is writing and documenting, because if you don't document it, nobody can look at it again, or like you can't pass on the knowledge that you just learned from the experiments you did. There's a lot of meetings and planning as well that happen. So all of this design work, it's not just you doing it by yourself. There's a group of us, there's engineers, there's research scientists that all sit together to design the new process and kind of put our input of the skills that we've had or the experience that we've had. And lastly, other writing that we do, which I've been doing quite a lot since we've been working from home, is writing operating procedures and safety documentation. It's probably the documents that everybody avoids a lot of the time, but it is really important because say if I was to leave and somebody wanted to operate the equipment, they wouldn't know how to operate it. They'd have to figure it out if I didn't have the operating procedure written out for them. And safety documentation, I mean, it's meant for us to be able to go home at the end of the day, so it is very important. So as I was mentioning, the first research area related to carbon dioxide is actually the capture process. So at CanMed Energy, we do have, I don't actually have the picture here of our system, but just to give you an idea, what we do is we have this tall tower that's an absorber, and you're taking the flue gas that's coming from an industrial plant or a combustion unit, and it goes through this absorber, where the absorber has a solvent inside of it. And well, in most cases in this type, it's amine based, and so the flue gas goes through the absorber and the CO2 is caught inside the solvent, and so the rest just then passes through, and then it goes to a second tower, and then the CO2 is then ripped from the amine solution so that you get this pure CO2. And so it's a common CO2 capture process that is out there, and people have been researching it. And there's different levels in terms of scale that are out there as well. But the reason we have it and the reason that it hasn't went to a very high industrial scale at this point is because there is a lot of research that still needs to be done. Some of them that I've listed here, some of the challenges. One of the ones we're really looking at right now is the degradation of the solvent. So over time, the amine inside the column, it'll start degrading into new chemical components that aren't either as effective at capturing CO2, or they become toxic, or yeah, they're not useful to what the purpose of your absorber is anymore. There's also the environmental aspect. So yeah, it's great we're removing CO2, but are we causing another environmental problem by the solvents that we're using as well? So you have to consider that as well. The cost is a big one. So in any process, if you design a process where it costs way more than what people are doing right now, there's no incentive to adopt this new technology. So there's always that in research. And another one, corrosion. Yeah, if you're building process equipment, you've got to make sure that you're not going to end up having holes in your system or whatever from corrosion of the solvent that's inside of there. I think that's all I can mention about that. If you have more questions about it, I can talk more about it. The next part, so after we capture the CO2, it's great. Like, we can keep the CO2, use it for whatever. A lot of the time people put it back into the ground. So CO2 sequestration is a common one. But the other side of it is you can try to convert it into something that's more valuable. So CO2 is not as valuable. When you put it into the ground, you don't get any value out of it either. But so we have another process where we take the CO2 and we actually react it with hydrogen. And the idea is to make some sort of hydrocarbon at the end of it. But what happens is inside this reactor module, so this is where a lot of my main focus since my PhD was on developing new catalysts. So inside this reactor is where the heart of my research is to create a catalyst that increases the conversion or the selectivity so that we're getting carbon dioxide out of the process. So then we can end up using this Fischer-Tropsch part where it actually converts it into, say, gasoline or diesel, so that it can just be put back into any of our cars. It's no difference than what's being dug out of the ground. Actually, I shouldn't say that. This process makes a more purified fuel, so I would say it's cleaner than what's dug out of the ground, but it's the same in terms of using it inside of your car. The other part of this process is not all of it will react, so maybe you get 40% conversion of your reactants going through here. And so we do have a part of our process where we actually separate the unreacted, so the CO2, from what we're passing to make the fuels. So we pass the CO2 back to the beginning so that we're recycling it back so that we can use it again and actually make it into the useful product. We're not just wasting it out the other side of it. And so this process, it's even, I would say, less mature than what I just showed you when it comes to capture. So a lot of industry has been doing CO2 capture, but they haven't been converting it into something like fuels, or when I say chemicals, you can make methanol from it, for example. And the reason for this is it is very energy intensive. So you're almost using more energy than you're getting out of it, which is where this motivation to create a catalyst that can decrease that energy requirement, so you don't have to run the reactor at such a high temperature. So that is one of the biggest challenges. The other one is making a catalyst that'll last long. So if we run the catalyst and it only lasts a month, you're constantly having to change and put new catalysts inside. That's going to bring up the costs, and it's not going to be affordable, or nobody's going to look at your technology in that case. So making something that will last a long time and you don't have to sit there and regenerate it. The last thing that is actually a challenge that we're still dealing with is, so during my PhD, I was doing bench scale research, so very tiny process, but this is at a larger scale. It's a pilot plant, and just going from that scale up into the pilot plant, it's been challenging. You can't just take the catalyst out of the small reactor, put it in the big reactor. We discovered a lot of different things, that the flow is different through the reactor. There's more piping, and so that affects how flow interacts with the piping as well. So yeah, it's not just, oh, it works at one scale, let's just increase the flow and increase the size of the reactor. It wasn't as simple as that, and so it makes it interesting, but it's challenging. And so the reason I'm sharing both of these technologies is that it kind of plays into this idea of what's called carbon recycling. So the whole idea behind this is, I know we're still producing fuels, but the idea is to actually not just burn the fuels in your car, let it release out into the atmosphere, because everyone knows about climate change, and that being not the ideal case is to just send CO2 out in the atmosphere. So if we can close that cycle where the CO2 doesn't go out into the atmosphere, we end up using it to convert it into another fuel, you put it back into your car, and you get this cycle going where we're not adding to the atmosphere, we're just reusing it in the system that we need. So as I was mentioning, there are some companies that are out there, but they're not that large of scale just yet. But if you're interested in this and reading even more about it, I've put some links here. I might have to actually share them with you to be able to click on them. But one big one is Carbon Engineering. It's out in British Columbia. And what they actually do is they take the air, or they take the CO2 from the air directly, so not even from post-combustion. They just suck it from the air, and they do the similar thing that we're trying to do. So they capture the CO2, convert it into, say, jet fuel. And so their whole idea is closing that loop of even from the air and putting it into, say, airplanes. The airplanes put it back into the air. So I don't know if you're interested in this. It is a really cool company to look into, and they keep scaling up, so they are going somewhere. Another one is Climbworks, and actually they're connected to what's called CarbFix. So this is actually, their plant is in Iceland, and they do similar thing as Carbon Engineering, where they're capturing CO2 from the air. But what they're doing is they're putting it into the ground, like I was mentioning, and actually creating rock. Cool thing about the company is you can actually buy rock in your name. So it's almost like buying a star in your name. You can buy rock that was from the CO2 from the air in your name. And just related to that is also Carbon Recycling International in Iceland. So they're even bigger, I believe, than Carbon Engineering in terms of scale. So if you're interested to see that even more, I would check out Iceland, or if you ever get to go there, check it out. And yeah, just showing you Carbon Recycling International. So instead of putting CO2 into rock, they actually create methanol. So when I was mentioning about converting it to chemicals instead of fuels, methanol is a chemical that actually is a precursor for a lot of other chemicals that are synthetically made. So if you can make methanol, you can then make every other chemical that you want from there. All right, so just to end off my presentation, a few things that I'd love to share with you is definitely don't think that you need to have a for sure plan, especially wherever you are in your undergraduate right now, because like I said, 4 years was my plan, go get a job, start your life kind of thing. It's not what happened. My life is not anywhere near where if I think back to like grade 12 going into university, not saying that it's a bad thing. It's more than what I actually thought I would do from the beginning, but just be open to what kind of comes at you and trying new opportunities. You probably hear this quite a lot, but I didn't know it until probably in graduate studies. So in undergraduate, I was quite shy. I went to my class, I went home, I did my stuff. I did not talk to as many people as I maybe should have in undergrad, but I learned that at least before I finished all of my schooling. But it is actually how I've been getting all of these opportunities. So even with my master's, the reason I ended up in the project that I was is because I went and talked to the professor. It wasn't, I just applied for the program and I got in. So that was that start. My job at Algonquin was talking to the professor that I was the TA for. Same with, actually Carleton was more, they found me on LinkedIn. So if you don't have a LinkedIn account, that's another way. It's sort of silent networking, I guess. And then NRCan, I did apply through their system, but it turned out that the group that I started in was actually in collaboration with my PhD supervisor, and so there was a connection in there that I just didn't know about until I got the position. But I highly recommend just any opportunity you can talk to people about where they're working, what they're doing. You may, don't always think that there's going to be something that comes out of it, but you never know, it could, so it's good to do. Another one, don't be afraid to fail. This was my biggest lesson that I had to learn. I was not used to, high school, I didn't fail any of my courses, and it was something that you had to learn. I wouldn't say necessarily just failing grades, but just trying for something and not getting it. Not to be too hard on yourself, because maybe you were just not meant to do that. And so there's been a lot of times where I had my heart set on something, I didn't get it, but you get another opportunity. So yeah, this little diagram, I've used it many years. It's more of what the path takes. You end up failing before you end up getting to the success. It's not just one road or the other that you go down. And the last one, do something that I would say makes the world a better place. It'll make you feel like you have a purpose in the world, instead of just finding a job that's just to do a job. There's a lot of opportunities out there that will make you feel like that, and you just got to keep trying to find it. But yeah, don't necessarily think that the first job you get has to be that. And so thanks for listening to my long journey, or at least my journey so far. And I'd be happy to take any of your questions, whatever it may be, from undergrad all the way up to what research that I do.
So thank you so much, Dr. Dole, for that great presentation and sharing your journey. It was really interesting. And it's really amazing to know that such research is happening in Canada. So yeah, we will be opening the chat box. So if anyone has any questions, please feel free to type it in or even unmute yourself.
I have a question. It might be a very long response though, so you can feel free to give an abbreviated version or ask me to talk to you later.
Sure.
So preface that I've actually been doing some work sort of in this field, like bench scale, in a lab. And I was wondering what specifically you were using as a catalyst and what the process was that you were using for catalyzing that reaction. Is it electrochemical? Is it heat? What kind of energy are you inputting?
So it's thermocatalytic, what we're doing at Natural Resources. The catalyst themselves is usually like a combination. It could be bimetallic or just single metallic on some sort of ceramic support. Trying to think of how I can tell you without telling you specifics, but does that give you an idea? Or
is it like a bulk metal on a ceramic support?
No, they're nanoparticle catalysts. So I'm making I would say under 10 nanometers, the metal themselves, and then it's deposited on the ceramic support.
Okay, sorry. That's pretty much the same thing that I'm doing right now with a different,
like different combination of metals or ceramics.
I've been using mostly gold, and we haven't been using ceramic. We've been using like carbon paper. But I don't know, similar idea.
Yeah. No, I did that actually in my PhD.
In like an electrochemical system.
Cool. Yeah, in my PhD, I was doing a little bit more electrochemical, or I don't know if you've ever heard of electrochemical promotion, where you have a electrochemical cell and you're actually changing or like moving electrons on your catalyst to try and change it. So either make it better, or I mean, you can make it worse in the same sense, but the idea is to make it perform better.
Mm-hmm. Yeah.
Okay.
Thank you.
You're welcome.
So there's a question in the chat.
I can't seem to open my chat.
Okay, so I can read it out.
Okay.
Curtis, going to your undergraduate co-op program, how would you suggest getting co-op positions within a research position or in a lab if you do not have previous research experience?
That is a loaded question. I mean, just trying to think of how I got. So my first position was actually outside of the co-op program. So I had just noticed, so I was looking for a summer job in first year university or after first year. And they were looking, this was at AECL, they were looking for student workers just on their website. And that's where I applied to it. I honestly don't know what they saw other than my grades from first year. But getting that first little position has, like, it was definitely what got me my next consecutive ones. So if you don't have that opportunity to like get that first one, you can even, I know we had in our lab as well when I was a graduate student, is you can ask professors to even volunteer in their lab. And even if you go, like say a half a day once a week, it might be kind of hard right now, but spend half a day with one of the master students or PhD students in their lab, because that you can then put on your resume. Even if you're not getting paid for it, it's still something to show them that you're interested in research, you've worked partly in the lab, and that's sort of, it's almost like you're trying to find a seed to kind of get the ball rolling. But other than that, I would say like the grades really helped me in the first year. Unfortunately, that's something that people look at quite a lot when you don't have work experience.
Great, so we have another question. What are some differences working in part of the government versus private sector? Example, the companies in BC, Ireland versus NRCan.
So I would say maybe short the pace of it all, because a lot of private industries, you're going to be like, I want to say working longer hours, but you could be working different hours. So you could be an engineer that's working shift work at private industry. The government is very much like throughout the day, like kind of 9 to 5, like plus or minus a few hours. I would say it's different in terms of like how things are funded as well. So private industry has a lot of investors so you may be like always, well, maybe not you yourself, but in private sector, like looking for investors, that's where their funding is going to come from. So in the government, they do have a program set out for whatever it is that their mission is when it comes to, well, in this case, natural resources. And so we do have a funding base. They still encourage us. So we do have industrial clients that we do have projects with. Just that is one big difference, is how things are funded. But some private industry as well, because they're so large, they may have an R&D section where when they're making products and making money off that, they're funding their R&D. So they may not necessarily need investors at that point, but the companies that I showed you, the research that like related to ours, they're all investor based. So it's a lot of, I would say, uncertainty in terms of funding.
Are there any other questions?
Would I be able to email you questions?
Sure. Actually, that's something that I should have put on my last slide. But Alika, if you want to share my email address, you can with the canada.ca one.
Thank you very much.
No problem.
I'll put it in the chat if that's okay with you.
Sure. Yeah. You can always, so all government employees have profiles online as well. So if you just search my name, I think you usually find me, but yeah. And I'm on LinkedIn, so if you ever want to connect and ask me questions there, you can as well.
It's in the chat. I have one question. So you mentioned that there are other industries and companies working on they have the same mission. So are you collaborating with any international companies?
So for our CO2 capture, we do have a connection to a company in the States, that they want to be using our system to test out their like the solvent that goes inside the towers. Our other projects, no, I wouldn't say international. So we do have one connection, but it's with a company that's out of Toronto. But there is interest in it, and the fact that we have like pilot scale facility, a lot of people do bench scale research, and then it costs a lot of money to build a pilot scale before you put it to like the industrial scale. And so that's where they end up coming to NRCan to test out their technology. Yeah.
Thank you. So I don't think there are any other questions.
Is NRCan the one that has the wind tunnel?
That's NRC, so National Research Council. The two of them get mixed up all the time. One's a department of the government and the other one is an agency of the government, I believe. So.
Okay, well, I added your email in the chat, so if anyone has any questions.
I think
And
there's one.
Oh.
Oh, there's another question.
Yeah.
What was your greatest challenge in doing your PhD?
Oh my gosh. I think I cried a couple times. No, no, PhD, what can I say? It's hard because you're trying to develop a new technology. And I would say this for actually a lot of research is you're trying to find something new, and most of the time it's not going to work. And so it gets kind of like you have to almost walk away from it sometimes and then like maybe come back to it and think of a new idea. But then it's almost you go to the other extreme. So the one day when my system worked or did something, I was like jumping up and down in the lab because it was finally working. And so my biggest challenge was just like getting the new thing that I was trying to do, because nobody's done it before. So you can't just go and find someone else that was doing it. You can talk to people and get their opinion on like where you should go next, but ultimately you have to figure out that new thing.
All right, so if that's all the questions, so before you guys leave, please take a few minutes to fill out the survey. The link I pasted in the chat box to give us feedback on how we can improve things and so on. And also, I believe the video will be posted on the YouTube channel, right?
Yes.
Yep. So if you guys need any more information you want to go over, feel free to check it out on the channel.
Yes. And we have another speaker coming in next week. So if you're interested, check out our Facebook page. But thank you everyone for joining our speaker series today. And again, thank you, Dr. Dole, for taking your time and talking about this very interesting topic. We hope to have you come back, hopefully in the future, for our speaker series. So thank you and have a good evening, everyone.